Hello, I'm Chris Kennedy. Today's space engineering lecture is a case study, the Habitat Demonstration Unit project that I was manager and led. So the Habitat Demonstration Unit project was really a unique project that formulated a multi-center team of NASA architects, space architects, scientists, and engineers working together to develop sustainable living quarters, workspaces, and laboratories for the next generation space missions. The knowledge gained from low Earth orbit projects such as the International Space Station and Earth-based analog research from the Desert Research and Technology Studies is being used in this project to find out what is required to expand human presence to more formidable environments like asteroid, Lagrange points, the Moon, or Mars. So let me give you a little background on this. So in the 2000s, mid-2000s, we did the part of the lunar architecture team, the LAT studies, and really we were looking at a lot of different options for lunar habitation to go back to the moon and establish a foothold. So we looked at it from the standpoint of concept of operations, human exploration of lunar surface with a crew of 4, install the science experiments, collect samples, and return samples. So the test science operation protocols and procedures in preparation for Mars surface mission. We also wanted to test the technologies and capabilities in preparation for the Mars surface missions. So there was 2 phases of the LAT studies, the lunar architecture team. There was phase 1, which focused on a singular surface architecture traceable to the specific objectives of the International Global Exploration Strategy. There was 2 human lunar exploration options. One, which is short sortie mission prior to permanent outpost, and then the second was outpost first. LAT 2 focused on refining the LAT 1 concepts and considered alternative architectures, a variety of viable architecture options. There were several assumptions, such as the lander could deliver 45 metric tons to lunar orbital insertion capability. The lander shroud was 10-meter diameter, or the launch vehicle. The mission frequency and duration was 2 flights per year, crew of 4, total of 180-day mission. And science capabilities was to have 500 kilograms delivered science payload and 10 kilograms sample return per crew mission. This is the design reference mission chart, which shows the concept of operations for the studies. You can see that you have your launch vehicles, both cargo and lander and crew, which rendezvous in low Earth orbit, perform the translunar injection, rendezvous or captures in low lunar orbit, and then descends to the surface, performs your surface mission objectives, and then the crew returns to low lunar orbit and then rendezvous with the Orion to be returned to Earth. This was the analysis trade tree that we performed. And you can see on the left there's the mission, exploration mode, site, outpost, and placement, fixed versus mobile outpost, and dedicated versus common. So this is how the trade tree analysis was done. We had from a mission perspective, we had exploration first, ISRU first, and placement and operations. And then each of those was broken down into, for exploration, you had crew exploration and dual mode exploration. From an ISRU perspective, you have the site, which would be polar, equatorial, or somewhere in between. And then we had to decide the outpost, whether we want predetermined or exploration determined. I think you understand the difference there. And then we had fixed versus mobile outpost. So you have a fixed outpost, stationary, in which you do your sorties and your exploration from that, or you have an outpost that moves around. And the mobile outpost really kind of is more exploration determined for your final location as opposed to predetermined. And then from a habitat perspective, we had separate habitat and mobility versus an integrated habitat and mobility. So we looked at these trade trees and tried to understand what options would be the best and satisfy the mission and science objectives of our analysis. So this is from phase 2, the lunar architecture studies. In option 1, lat 1, phase 1, the philosophy was for a stationary outpost for 4 module outposts with solar power generation. Option 2 focused on mini habitats, the philosophy of a modular small mini habitats that could be brought together using smaller landers and smaller launch vehicles. Option 3 was a large monolithic habitat, the philosophy of a single large volume, pre-integrated and outfitted outpost that could be landed in a single lander, a large cargo lander, and then simply surface construction ops. That way you simplify the surface construction ops, having to put modules together, align them, and then burr them and bolt them together, etc. And option 4 was a mobile lander habitat, the philosophy of a fully functional crew lander habitat combined that could traverse on the lunar surface. This would employ a module integrated design for simplicity of operations, flexibility, and wide-ranging capabilities. Option 5 was early delivery of pressurized rovers. The philosophy here is of enabling long-range surface exploration as early as possible, and the crew would live within these pressurized rovers, understanding and the constraint that there is time limitation how long the crew can live in these small pressurized rovers, even if you linked several rovers together. And then option 6 was a nuclear power, variants of option 2 and 3 that use nuclear power rather than solar. So here's kind of that breakdown, a chart showing the different configurations of the options as I previously discussed, the number of elements for each option, how large the habitats were, the total pressurized volume, the floor area that was produced in these different configurations, the total mass, power that was required to operate, and then also the number of available ports, which turned out to be important to be able to connect or have visiting vehicles and so on. And then the outfitting strategy was pre-integrated or some outfitting was required. So the mobile hab lunar architecture really was about making use of the triathlete. So the JPL concept, the triathlete, was a mobile platform system that has robotic mobility legs that can lift off the lander, lift the payload off the lander, and deliver to the surface, and then separate from the payload and delivering a module to the surface, as you can see here. And this was a horizontal module. So the has the integrated functions of power support unit, such as power source, batteries, and fuel cells. So this was a picture of the mobile hab lunar architecture, which is one of the focuses of our rapid prototyping and analog development. We want to look at the aspect of mobile architecture utilizing this idea of pressurized rovers and a science research module that could be moved from the base and do remote locations. We looked at two different sizes or two different shapes. We looked at a horizontal cylinder with an integrated pallet arrangement, and we also looked at a tuna can cylinder, if you will, with an inflatable airlock integrated to it. This was the architecture that we ended up building the rapid prototype to look at the concept of operations in the Desert Rats activity And so we built this horizontal, not the horizontal, but the vertical CAN approach. That's the background behind what led to the Habitat Demonstration Unit project, which was really a grassroots effort to pull together NASA experts and rapid prototype and develop the systems to be a forcing function to get the technologies off the benchtop and into integrated testing. So the Habitat Demonstration Unit overview is that it was a vertical cylinder habitat was established as an exploration habitat testbed platform for integration testing of a variety of technologies and subsystems that would be required in a human-occupied planetary surface outpost or deep space habitat. The HDU functioned as a medium fidelity habitat prototype from 2010 to 2012 and allowed multidiscipline teams from all over NASA to collaborate on field analog missions, mission operations tests, and system integration tests to help shake out equipment, technologies, and provide feedback on technology development cycles and crew training. Though much of the higher fidelity functionality has graduated into other NASA programs, the HDU project was canceled, taken over by the Human Research Program, and renamed the Human Exploration Research Analog, HERA. And here's the link here. It continues to be available as a volumetric and operational mock-up for the Human Research Program since 2013. So one of the unique aspects of this, in 2009 we had the PowerPoint concept sketches of what this pressurized excursion module is or was. And within a year, we went from PowerPoint to an actual physical demonstration unit, an operational unit in the desert in August of 2010. And then in 2010, we continued and matured from the aspect of a deep space habitat, which was NASA's focus at the time, and how we could transition the HDU to have some functionality and some of the attributes of a deep space habitat that we could test from a concept of operations perspective. The other aspect that came out of this is we started up and developed the Academic Innovation Challenge, or the Exploration Habitat XHAB Challenge, for universities to participate with our work and efforts. So I developed a habitat strategic vision and interdependency, and tried to map and show those interdependencies of all this work that was going on throughout NASA, and show the relevance of what we were doing and how this could lead to a spaceflight demo. So this was done back in 2009 timeframe, in which case we were looking at the technology roadmaps from TA7 and TA6. I led the TA7, which was Human Exploration Destination Systems. From that, that was a focus of the Office of Chief Technology for Exploration Technologies Development. And this allowed us to focus and collaborate and leverage other projects that are going on to take and mature and infuse those technologies into our demonstration unit. Then we looked at it from the standpoint of the AES, Advanced Exploration Systems Habitation Project, and looked at developing a generation 1, 2, and 3 over time, maturing and getting higher fidelity, and then eventually leading to a 20-foot chamber closed door test with crew inside at lower atmospheric pressure. From that, we determined that it would develop into an ISS flight demo that could be placed on ISS and shown to work. So one of the things we want to do in any project is talk about the benefits to the Human Exploration Operations and Missions Directorate and the architecture. So this effort, the Habitat Demonstration Unit, had the benefit of mission architecture validation. So in the utilization of deep space habitat within NEO exploration architecture, to help with operations concept validation, to help and understand the risk mitigation, to learn by doing and advanced technology concepts. Technology maturation and infusion, which was very important to capitalize on investments into technologies, but be a forcing function to get those technologies off the benchtop and into integration and testing. It was a multi-center advanced habitat team, which actually became a team that stayed together and helped and developed into the deep space habitat, and then went on to help with the development of some of the gateway products. It forced an interagency collaboration to synthesize research and advance from different and multiple agency interests, as well as international collaborations that laid the groundwork for international cooperation on long-term space projects. And then it was a huge STEM activity for education outreach and public engagement. It became a very important part of our strategy in how to engage the public and the universities. So, there are HDU interdependencies, such as the human exploration architecture, the concept of operations and concept, the definitions and validations. The multi-mission space exploration vehicle shared commonality and modularity. We also shared interdependency between the other HAB-related projects, as well as the Office of Chief Technology and Technology Developments. The platform to focus and pull technologies into integrated testing, a focus on avionics, software, life support, and habitation. And also the aspect of future advanced habitat systems. We were also able to pull into the human research program to help and focus on some of their testing, and from the aspects of participatory exploration. The X-HAB University challenged multiple universities designing systems, and not just designing systems on paper, but actually having to follow the NASA process, build the systems, test them, and then deliver them to be integrated into the HDU. And also it performed a forcing function for the technology roadmaps. So here's the dependencies for the collaboration and leveraging that we performed with all these different entities. Some of them were more peripheral, and some, like the yellow ones and the green ones, had direct connection to specifics that we could pull into the Habitat Demonstration Unit and show these and integrate these technologies. This was our roadmap, or our plan to get to flight demonstration. It showed the different technology from a technology development perspective, and all the different technology areas that were being worked on and developed, and showed at different points for the different generational units: HDU Gen 1, which was operational demo unit, Gen 2, and Gen 3. And how each of those would then be brought into the integrated testing and eventually to a flight demo, which was canceled, obviously. Let's talk about the project itself. So the vision was to develop a fully autonomous habitation systems that enable human exploration of space. The mission was to develop, integrate, test, and evaluate habitation systems that will be utilized as technology pull and test beds, and advance NASA's understanding of alternative mission architectures, requirements, and concept of operations definition and validation. The Habitat Demonstration Unit and the Deep Space Habitat Configuration would be ready for testing in July of 2011. These were the project objectives for HDU. To provide a capability or a platform for lean management team approaches and rapid prototyping in skunk work environments to develop and validate mission architectures, concept of operations, and requirements. It also provided an opportunity for young engineers and architects and scientists to work together to learn from older, more seasoned veteran engineers, and be able to really build upon the NASA legacy of building and testing and learning. It also provided a capability or a platform for integration of internal subsystem hardware and software needed or required for exploration habitats, independent of the shell shape. And that's important because a lot of our focus, management focused on the shell shape because they were trying to sell it. We were focusing on the guts of the system, the operations of the system, the hardware and software, getting it ready with a human-centered design approach. It also provide a platform for implementation of autonomous operations, monitoring, and control. And so really we tried to focus and develop that autonomous operations capability. Again, focusing on the internal aspects of the systems and getting it operational. Another objective is that it provides a platform for participatory exploration through the X-HAB University competition. It provided a platform for maturing HAB integration team for future habitat design efforts. It provides a ground-based platform to integrate ISS subsystems with future technologies. It provided a ground-based platform to access affordability approaches of modularity, commonality, reusability, and repurposing. As well, it provided a ground-based platform for technology infusion. One of the key aspects that we developed during this process was defining a deep space HAB traceability matrix. What were the key test objectives? What are the key habitat questions for deep space habitats that we really need to better understand? And so we labeled them all, and the ones highlighted with yellow and the green arrows are the ones we were addressing in the Habitat Demonstration Unit. These are important key questions that have a traceability towards the derived requirements for future missions, and they cover everything from EVA operations to autonomous HAB operations, logistics, maintenance and spares, habitable volume, crew operations, mission operations, medical operations, geoscience operations, life support closure, sufficient stowage volume, radiation protection, life science research, lightweight structures, power management distribution, and environmental protection. These key 15 questions are important aspects of architecture traceability and test objectives. So 2010 HDU, the Pressurized Excursion Module test objectives and deliverables. Our top test objectives were: the architectural objective was to validate the use of the PEM as described by the scenario, Lunar Scenario 12.1 architecture. So we had specific hardware objectives and operational objectives, and you could read through them. But a few key aspects was to perform a shakedown assessment of the integrity of the HDU after a long haul transportation to the field, and perform successful in-field installation. So these were specific objectives that had to do with the actual HDU unit itself. They would perform successful checkout and dry runs in FY010, perform successful evaluations of the workstations within there, provide reliable autonomous command and control capabilities, provide reliable utility services such as thermal conditioning, power, and communications, evaluate geoscience laboratories and glove box, and evaluate use of EVA maintenance areas. Operational perspectives: from the concept of operations, we had numerous items, objectives that we wanted to satisfy. A few of them was integrated test mission operations, standalone test mission operations, logistics and waste management, human factors assessments, effectiveness of dust mitigations, etc. In continuation of the objectives and deliverables, the technology So additional test objectives is technology demonstrations. We had numerous technologies that we brought to and integrated that which we want to demonstrate. Our success criteria metrics was geologic samples process and crew time to process samples, to understanding of that, an understanding of crew time to manage logistics and waste, the protocols and the concept of operations of doing that, understanding the dust contamination levels of the interior, and overall acceptability of the PEM features and functionality. The deliverables included subsystem performance data, integrated system and performance data, human factors data, field operations logistics data, and the final report. In 2011, we upgraded and did additional test objectives and deliverables to the habitat demonstration unit with a focus on deep space habitat characteristics and design. So we had specific hardware objectives. Again, our architectural objective was to validate the Deep Space Hab operational role in a human exploration mission scenario to an asteroid. Our hardware objectives had to do with the in-field installation, checkout and dry runs, evaluations of workstations, evaluations of providing reliable autonomous command and control capabilities, and then the services. So from an operational objectives, we again were performing an integrated test of mission objectives and standalone test objectives. And these were our deliverables, similar to the previous. So the Deep Space Habitat demonstration included an inflatable loft, which the original Deep Space Habitat design had an upper loft inflatable for the habitation or habitat living portion functionality, and the lower part, the metallic part of the shell or composite, was the laboratory area. So we looked at demonstrating autonomy, operating kind of the moving towards a smart habitat. We looked at sustainability and supportability technologies to reduce sparing and logistics. We looked at logistics to living outfitting, which really looks at the aspect of looking at cargo transfer bags, CTBs, and how they could be reused or repurposed to make partitions or make furniture or a number of things. We looked at different aspects of deployable outfitting. We looked at telerobotics workstations and telemedicine systems. In addition to that, we looked at radiation systems, in situ parts manufacturing capabilities, advanced fabrics with integrated radiation protection and biotechnologies. We looked at advanced ECLSS systems for long duration spaceflight and dual chamber inflatable hybrid suit locks incorporating suit boards. These were all of the different technologies and innovations that we demonstrated in 2011. It's hard enough to get one technology off the benchtop and into an integrated test, let alone 21. And so we had an amazing amount and a great team that pulled together and integrated all these different technologies into an operational demonstration unit. And it was amazing. It really became a forcing function of technologies for technology infusion to find out what was working and what was not working, how to improve, and then to derive requirements for better systems in the future. This was our 2011 configuration for Deep Space Hab. It had an airlock where it had capability for 2 rovers to dock to it. It had an inflatable loft. We also had a hygiene module. And you're probably wondering, well, why this configuration? In part, we were making use of existing assets that were already built at JPL and JSC and other locations at NASA. And so the only thing we built was the bottom shell, and then we used for the inflatable loft, we used the XHAB challenge for universities to propose, build, and demonstrate in a head-to-head competition of the XHAB or the loft. The airlock or dust module was, like I said, these were some existing assets that was already used on analog ground testing, and so we made use of them. The one thing about when you develop an analog test bed or capability is you don't always have the funding or time to build everything just as it would be in space or flight-like. You have to make use of capabilities and existing assets that are here already and incorporate them into it. So it becomes an alignment of functionality on paper, but as a ground analog test bed does not necessarily look flight-like. This was our how we organized and laid out the different sections and areas within the module or PEM excursion module, which had 4 workstations: a geolab, medical ops, maintenance, and teleoperations. And then above it had the inflatable loft, which had the living part of exercise, logistics, galley, wardroom meeting, and workstation, as well as then the 4 crew member sleep area above, the crew pods. So these are some of the test configurations, the graphics of the modeling that we did. As you can see down here, we actually used external air conditioning units and used air ducts to pump in to have the air system. Since we did not have Eclipse systems, ISS or otherwise, available to us, we used just Earth systems. We did not necessarily try to make those flight-like. And that was the trade-off. That's the trade-off of performing these kinds of analog tests, what you can get for what you have budget to do. This is the interior configuration showing some of the workstations, the maintenance workstation. This is the geo box over here, the glove box. And also what was unique is in zero gravity, you'd be able to flow up through into your loft space. On the lunar gravity, partial gravity, you would need some stairs to go through there. In our Earth analog test bed, we actually had to put stairs and a platform to move equipment. So we actually had a man lift or a person lift to be able to move equipment up into there. This is the integrated field test analog with all the different equipment that was out in the Desert Rats. The location was north of Flagstaff towards the Grand Canyon. Because of the lava outflows of that location, it has a lot of similarities to Mars. So as we were looking to do our exploration concept of operations and protocols of handling samples, this is what we used. And this year in 2010, you can see the loft was not on here, so we just had plastic covering the top of it. But we did have the airlock that we used and borrowed. We did have the logistics module as well as the athlete system. And this is the project team that worked on this, including myself and a couple other people from other centers, Terry Tree, Tracy Gill, and Scott Howe. So the demonstration unit for Deep Space Hab then changed. It had everything that we had previously, but we added the inflatable loft. And the thing about the inflatable loft is, no, it was not flight-like. Matter of fact, it did not even look great, but it was functional. You could actually go up in there and live in there and sleep in there, etc. And the University of Wisconsin is the team that won that head-to-head competition. This is Scott Howe inside the pressurized excursion module. This is the human lift here. That's how we got equipment up and down. We also took advantage of the space and actually put in food growth systems here. Within this annulus, we had drop-down stowage, We had a track system to move heavy equipment around. We had the medical bay, we had the ISR, we had the maintenance bay, telerobotics workstations, etc. This is the geoscience laboratory or glove box that was actually an operational unit, and this was part of a leveraging and collaboration with the science community. Another picture, this is up in the loft showing the stowage, the galley area, the work areas, not work areas, but the dining areas, and then the loft was up above, in which the second phase we did improvements to the loft to create, and we collaborated with the U.S. Army Natick Research Center to create these deployable lofts, or the crew pods that later changed out from what this is shown here. This was the human factors data collection measures. You can look at the different areas of human-centered design, human factors study, the different aspects that they were looking at, different workstations, the operational ability of it, the crew workload, different aspects. And then here were the measures for the data collections and the scales that were used, as well as the frequency. Here's some of the data generated from the analysis, and the acceptability, borderline, or unacceptable, all the different criteria and areas that were looked at, and you can see how they turned out. So acceptability of the PEM workstation displays and controls was unacceptable. The design of the PEM trash management system was unacceptable. The design of the PEM inventory management system, unacceptable. And this was important data because now we can look at and derive our requirements, redesign our systems to better functionality. This was some of the pictures from the GeoLab testing and operations, looking at the rock splitter, the outside on the bench, EVA sample retrieval techniques, looking at camera placements, handling and processing protocols of the samples, design and layout, and the GeoLab operations. So in summary, the deep space habitat functionality and operational test bed. So we did do that, we performed that, we did those tests, and it really helped us to better understand what is needed for these exploration missions. We were able to sync habitat goals with human spaceflight architecture team. We were able to maturing the test objectives in coordination with the human architecture team. We were able to do the participatory exploration via the XHAB challenge, which is still going on today, 11 years later. We were able to infusion of the Office of Chief Technology Exploration technology development activities and get them off the benchtop and into testing to mature their TRL levels. We also were in collaboration with other advanced exploration systems, which became an important aspect and showed that we needed to do this in other areas and bring other systems together and focus on integrated systems testing each year, and then the integrated mission testing to further define and understand the protocols of the concept of operations, and then pushing towards an ISS Deep Space Hab testing prior to a deep space mission. So in summary, the deep space or the habitat demonstration unit project was very successful. Even though it only had lasted 2 to 3, 4 years, it was a unique opportunity, a grassroots effort as how it formed with myself and a couple of folks that became part of the management team. And we really became a focal point to bring together these architects, scientists, and engineers working together to develop these spaces, these workspaces and laboratories and sustainable living quarters. And this knowledge was tremendous, and it helped us to really understand both the human in the loop testing, as well as forcing function for technologies. Thank you. I hope you did appreciate this case study.